This is example 6-5, an accelerating balloon. So we have this nice little red balloon here, and we're given that it has a mass of 20 grams, so we adjust the balloon itself, and it's filled with air at a temperature of 20 degrees C, and when it released, it accelerates at 8 meters per second squared. And now we're supposed to find out what the initial mass flow of air is out of the balloon. All right, so with that, we will probably have to give ourselves a free body diagram of the balloon. So let's take the entire air that's inside of the balloon. So something more or less of a circle, and then kind of the stem where the air is flowing out. Maybe we'll call this A, and of course the only force that's acting would be the weight of the balloon. There we go. All right, so that's our free body diagram. Now let's figure out the rest of the stuff that we need. So we have an accelerating body, right? That means we have to write our linear momentum equation with acceleration, which means we will need to know the mass. And of course, we'll need to know the weight as well, because we have it here. Let's start with the mass. So we can say mass of balloon plus air. Right, because both of those are being accelerated. So that would mean, well, I guess before we can get the mass, we have to know the density, so we'd have to look that up. Go to the table and look up that at 20 degrees C, density of air would be rho is equal to 1.202 kilograms per cubic meters. Now we can get the mass, right? So we can say mass is equal to mass of just the balloon plus the mass of the air. Mass of balloon we're given as 20 grams, so that's 0.02 kilograms, and then the mass of the balloon is going to be the volume times the density. So density is 0.02 kilograms per cubic meters, and then this is a sphere, so that'd be 4 pi over 3, and then the diameter is 300 millimeters, 0.3 meters cubed. And that gives me a mass of 0.155943 kilograms. So 156 grams is our mass. All right, so we have the mass. Now we need the weight of the balloon. So the weight is different than the mass here. So we're not just going to take the mass and multiply that by g, because of course the air that's inside of the balloon is canceled out by its buoyancy, right? So we don't have to worry about the air inside. We just take the mass of the balloon. So weight of balloon without air would be W is equal to M times G. I guess put a B in there. So that would be 0.02 kilograms times 9.81 meter per second squared. And that gives me 0.1962 Newton. Okay, now I have the weight and I have the mass. So now I can write my linear momentum equation. So my linear momentum here equation with acceleration, right? That's then the sum of forces is equal to mass times acceleration. Acceleration will say the velocity of my control volume dt plus my regular linear momentum equation, control volume v rho dv plus integral over the control surface of v rho v dot dA. And then we can simplify that, right, because we have a steady flow. So for steady flow, ideal fluid, uniform velocity profiles. Well, if we do all that, then our equation simplifies to be, well, we drop one term and turn one integral into a sum, right? So we'll have that acceleration term stays the same, divided by dt plus 0 for our time rate of change, and then we have v rho va. All right, so if we do that for our very specific case, the vcv dt plus, so where our control surface, my control surface is going to be right here. Going to have my area pointing out, my velocity is going that way too, so I'll be positive, so I'll be VA times rho AA times VA. All right, so that is good. That would be our general equation. Now we're only interested in the y direction, because the only forces we have are in y, the only flows are in y. So we can write this in the y direction. Probably should put a little coordinate system here, x, y. So then we can write, we can say sum of forces in the y direction. That's what we have up there. So mdc control volume dt. Now our VA vector is pointing downward, our y is pointing upward, so it'll be negative, minus VA rho times AA VA, right? That's positive because they're both going in the same direction. All right, so can we simplify that somehow? We can pull that V out, I guess, right? So we can say equal to M D, why is there a C there? That makes no sense. Be a V. There we go. VCV dt minus VA squared rho AA, right? That's our flow contribution. Now the forces, we only have one force, that's the weight. It's pointing in the negative direction, so all of this equal to minus W. Now we want to get the mass flow rate, so we have to have the velocity at the exit there, right? So solve all this for VA squared, right? So we can say VA squared, so bring that over and that over, would be M times D VCV over dt plus W divided by rho AA, which of course is then VA is equal to the square root of that mdv CV over dt plus W over rho, and A is of course pi over 4 times dA squared. Plug those values in, and we get something big, right? So our mass that we calculated, that was the mass of the balloon and the air, was the 155. So that is 0.155943 kilograms. This term here, the dvcv dt, right, that's our acceleration. It's given to us as 8 meters per second. 8 meters per second squared, I'm sorry. 8 meters per second squared, that's our first term. And then kW was 0.1962. 0.1962, and that's Newton. We divide that by 1.202 kilogram per cubic meters times pi over 4 times the diameter is 5 millimeters. 0.005 meters, and that's squared. And that gives me 247.3306 meters per second. So the air is coming out there pretty fast. All right, we're not asked for the velocity, we're asking for the mass flow. So we just have to multiply that by the area and by the density. So we can say the mass flow is equal to rho times V times AA. Let's say VA. That is 1.202 kilograms per cubic meters times 247.3306 meters per second times pi over 4 times 0.005 meters squared, and that gives me 5.8373 times 10 to the minus 3 kilograms per second. Or we can write that as 5.84 grams per second. That would be our mass flow rate coming out of the bottom of our little balloon as it's accelerating upward.